I'm going to calibrate the Radiacode's energy spectrum using the BecqMoni Nuclear Edition app. In Edit Device Configurations, you can add your device. My device is already added, but let's go through the steps for adding a new one. Here, enter the name you want to give your device. Then select Radiacode. With the device on, search for it by Bluetooth. Once connected, go to the Energy Calibration tab and read the device's calibration coefficients. These coefficients will be used to establish the relationship between the channels and the radiation energy using a second-degree polynomial function, where the energy of each photopeak will be determined using a Gaussian fit. In order to initiate the spectrum measurement, we will create a new file. And finally, we press Start. Because my device isn't on, I need to turn it on first. Now I can press Start, and the Bluetooth connection between the application and the added device is immediately established. Once the spectrum acquisition is complete, we just have to stop it and save it. Let's start the calibration using thoriated tungsten welding electrodes, as suggested by Radiacode. Here, we have two sets of electrodes with the same dimensions. One contains 2% thorium, the WT20, red tip, and the other contains 4% thorium, the WT40, orange tip. To maximize the count rate, we'll use both, stacking them with the more active one on top. This way, a high-quality spectrum will be obtained in less time. Now, let's position the device over the electrodes, with the bottom facing them, ensuring the plus sign marked on the bottom is facing the radiation field. Let's start the spectrum acquisition. Next, let's restart the acquisition to clear the previous run and start a new one. It's important to note that the Radiacode user manual recommends keeping the count rate below 500 CPS during calibration. At high count rates, pulses overlap, increasing dead time. This causes pulse pileup, where multiple events appear as one higher energy pulse, distorting the spectrum. Let's select the thorium-232 region of interest for guidance. Since we want to visualize a spectrum that includes low, medium, and high energy photopeaks, I chose the power scale to improve visualization. By default, photopeaks are displayed once they reach a minimum signal-to-noise ratio, SNR, of 10. The identification of the radionuclides is displayed in this column. In the next column, we see the measured energy. The following column shows the energy error relative to the reference photopeak. After that, the associated channel is displayed. The second-to-last column shows the signal-to-noise ratio, SNR. And finally, the full width at half maximum, FWHM, in both absolute value and percentage. The SNR is a key indicator of photopeak quality, increasing over time as counting statistics improve. For this calibration, we will extend the acquisition time so that the photopeaks of interest achieve an SNR of 20 or higher. Achieving high SNR values within a reasonable time frame is highly desirable. The full width at half maximum indicates the detector's energy resolution. The photopeak energy is taken from the centroid of the Gaussian fit, while the full width at half maximum is derived from the distribution's width. Upon completion of more than 14 hours of acquisition, a high-quality spectrum was obtained. The first photopeak identified is the crystal escape peak. The second photopeak, mistakenly identified as americium-241, is actually the tungsten X-ray fluorescence XRF peak. The following photopeaks come from the gamma emitters in the thorium-232 decay chain. With the exception, of course, of this peak identified as bismuth-214. We will select the tungsten XRF peak as the low-energy calibration point. We will select the thallium-208 peak at 583 kilo-electron volts as the mid-energy calibration point. And finally, we will select the thallium-208 peak at 2,614 kilo-electron volts as the high-energy calibration point. In the Energy Calibration tab, we will click on Multi-Point Calibration. The three added values are listed here. As indicated in the Radiacode procedure, it will be necessary to change the energy of the mistakenly identified peak to 65 kilo-electron volts. And now, we can execute the calibration by clicking on Execute Calibration. Energy calibration is done. By clicking on Graph, we can view the calibration curve along with the selected calibration points. Returning to the Peak Detection tab, we can see the new energy errors. The energies of the correctly identified photopeaks now display zero error. The calibration could be finalized at this point. However, we will try to improve it further. The 583 kilo-electron volt thallium-208 peak is weak and distorted by nearby bismuth-214 interference, as well as by the Compton continuum from higher energy emissions, especially the 2,614 kilo-electron volts thallium-208 gamma, making it less reliable for calibration. Let's consider the 662 kilo-electron volt gamma emission from cesium-137, originating from the spark gap of an antique electronic device. Once again, it is essential that the plus mark on the detector base remains aligned with the source and facing the radiation field. To increase the count rate, we can move the detector closer to the surface of the spark gap. In this way, the spectral acquisition will be faster. We start by creating a new file. And then we start the new spectral acquisition by pressing Start. Following that, we restart the acquisition by pressing Clear. For guidance, we can select a more convenient region of interest. And finally, we can enable the automatic photopeak detection. The 662 kilo electron volt photopeak has quickly reached an SNR of 10, and that ratio is continuing to improve as the acquisition time increases. In about 2.5 hours, we obtained a high-quality spectrum. The 662 kilo electron volt photopeak of cesium-137 is sharply defined and has a very high SNR, making it a more suitable choice as a mid-energy calibration point. On the other hand, this is the energy commonly used to calibrate radiation monitors for dose equivalent rate. Finally, cesium-137 is a key long-lived gamma-emitting contaminant arising from nuclear accidents and weapons tests. These three aspects make the 662 kilo electron volt photopeak a preferable calibration point in terms of measurement accuracy. Let's add it to the detector's calibration. We will now access the previously saved thorium-232 spectrum. And we will add the tungsten XRF peak as the low-energy calibration point. And then the thallium-208 photopeak at 2,614 kilo electron volts as the high-energy calibration point. In the Energy Calibration tab, as before, we adjust the energy of the tungsten XRF peak to 65 kilo electron volts. Now we click on Get All Points to add the cesium-137 662 kilo electron volts photopeak. And finally, we perform the new calibration by pressing Execute Calibration. We can now proceed in the same way with the cesium-137 spectrum to verify the calibration errors obtained from this new calibration for this spectrum as well. As expected, the measurement error for the 662 kilo electron volt photopeak is now 0. The same occurs for the 2,614 kilo electron volt photopeak in the thorium-232 spectrum. The measurement error for the 583 kilo electron volts thallium-208 photopeak increased, but it remains lower than the error found for the 662 kilo electron volts photopeak before calibration. In Part 3, we will consider several sources. Let's start with a radium-226 source from the radium paint of an antique watch, which can also be found in certain antique shops. Once again, the detector should be positioned with the plus marking on its base facing the radiation field. keeping the distance between the source and detector as short as possible within the recommended count rate limit. Once again, we start by creating a new file. Then we proceed as before, starting the acquisition. As before, for guidance, we can select a more convenient ROI and enable automatic peak detection. The gamma emitters of the radium-226 decay chain are now starting to be detected. In about 5 hours, we obtained a high-quality spectrum, where the gamma emitters of the radium-226 decay chain were detected. With the exception of radium-226, mistakenly identified as uranium-235 due to the proximity of their gamma emissions, the detected gamma emitters arise from the decay of radon-222, a radioactive gas. From this decay chain arises lead-210, a long-lived radionuclide characterized by a low-energy gamma emission at 46.5 kiloelectron volts. Being a low-energy photopeak with a very high SNR, it serves as an excellent calibration point for the low-energy region of the spectrum. Let's add it to the calibration as a low-energy calibration point. In the thorium-232 spectrum, we'll re-add the thallium-208 photopeak at 2,614 kiloelectron volts as the high-energy calibration point. In the cesium-137 spectrum, we'll re-add the 662 kiloelectron volt photopeak as the mid-energy calibration point. And now we'll perform a new calibration using these 3 calibration points. This results in the new calibration coefficients. Let's see how the measurement errors look for the other spectra. As expected, the measurement error is 0 for the 2,614 kiloelectron volt photopeak. As expected, the measurement error is 0 for the 662 kiloelectron volt photopeak. The error associated with the 32 kiloelectron volt peak has decreased, and the application now correctly identifies it as associated with cesium-137. As expected, the measurement error for the 46.5 kiloelectron volt photopeak is 0. The error associated with the radium-226 photopeak has decreased, and the application now identifies it correctly. A final note. The 609.3 kiloelectron volt photopeak of bismuth-214 is well defined, and has a high SNR, making it a suitable alternative to the 662 kiloelectron-volt cesium-137 photopeak as a mid-energy calibration point. LiSo crystals and metallic lutetium both contain about 2.6% of the radioactive isotope lutetium-176, which emits beta and low-energy gamma radiation. LiSo is a scintillation crystal widely used in radiation detection, particularly in positron emission tomography (PET) scanners and other high-resolution gamma imaging systems. Metallic lutetium is a dense, rare earth metal and one of the least abundant naturally occurring elements. Their intrinsic activity provides a natural background useful for detector calibration and performance checks. To increase the count rate, we use both samples together. And once again, the samples were placed over the plus marking on the detector base, ensuring that the radiation field is directed along that orientation. Since the activity of the samples is very low, we will place the detector with the samples inside a 4 mm thick well-type lead shielding. This setup significantly reduces natural background radiation in the low-energy part of the spectrum, since 4 mm of lead absorbs most low-energy photons, where the photoelectric effect is the dominant interaction. Now, we proceed as before and create a new file where the spectrum will be acquired. And we start the spectral acquisition, clearing any residual spectrum previously accumulated. The prominent lutetium-176 photopeaks rapidly reach an SNR of 10, enabling a reasonably clear identification of this rare, naturally occurring radioisotope. The SNR will increase with acquisition time. After 12 hours of acquisition, a high-quality radiation spectrum was obtained. An annihilation peak is identified, which is actually a sum peak of the two gamma radiation photopeaks of lutetium-176. We will now perform the calibration using the new calibration points obtained from the previous spectra. Lutetium-176 was clearly identified in all three peaks, with no unacceptable measurement errors. The check test is complete. A final note. The 55 kiloelectron-volt X-ray peak of lutetium-176 provides an alternative low-energy calibration point. Now we move on to another check test using an americium-241 source, which is also a low-energy gamma emitter. In the same way, we start a new acquisition. Start. Given the higher count rate and the low energy radiation, for which the detector is more efficient, the Americium-241 photo peaks are promptly detected. After about 12 minutes, the acquisition was stopped. A check before the new calibration shows that the measurement errors are low for these energies. Although the measurement error for the Americium-241 photopeak at 59.5 kilo-electron volts has increased, it remains low. As in the previous case, the 59.5 kilo-electron volt Americium-241 photopeak can also be selected as the low-energy calibration point. As a final refinement, we will use a sample of potassium sulfate, which contains about 0.0117% potassium-40, a naturally occurring radionuclide that decays mainly by beta- emission and partly by electron capture, the latter accompanied by a characteristic gamma line at 1460.8 kilo-electron volts. We follow the same procedure for the new spectral acquisition. And we select an appropriate ROI for guidance. Since we are interested in visualizing a higher energy photopeak, we'll switch to the logarithmic scale. After 3 days and 8 hours of acquisition, we obtained a high-quality radiation spectrum. If a fourth calibration point could be added, this would definitely be the choice, as it provides an intermediate energy photopeak between the mid and high ranges, with a high SNR. As observed, the measurement error of the potassium-40 photopeak decreased significantly after calibration. We now have zero error for the high-energy calibration point, where the photopeaks are broader. Which translates into a higher full width at half maximum, FWHM. Low and mid-energy peaks are more abundant in most spectra, such as environmental, medical, and norm measurements, when compared with high-energy peaks. Low and mid-energy peaks are also more affected by detector nonlinearity and electronic drift, so ensuring high accuracy in this range improves the overall calibration reliability. In quantitative spectrometry, relative intensity and isotope identification also depend more critically on the accurate positioning of low and mid-energy peaks. On the other hand, at high energies, the spectrum typically has fewer peaks and less overlap, so small deviations have less analytical impact. The percentage energy error, defined as the ratio between the absolute energy error and the reference energy, is smaller at high energies than at mid and low energies for the same absolute error. Therefore, having a non-zero error at the high-energy calibration point is not as critical. Let's now proceed with a refinement of the calibration using the potassium-40 spectrum as an upper-mid energy of interest. We'll slightly increase the error at the high-energy calibration point, shifting it down by 4 channels, in order to improve the calibration accuracy at the potassium-40 photopeak. The error became smaller. Let's now check how the error looks at the high-energy calibration point. The error increased by about 10 kilo electron volts, which is not much, and given this absolute error, the percentage error remains very low. This error is acceptable, as are the others observed within the decay chain. Let's now take a look at the cesium-137 spectrum. The energy measurement errors remain low, being necessarily 0 for the 662 kilo electron volts photopeak of cesium-137, since this peak was used as a calibration point. Using the InterSpec app, we can also check the calculated position of the Compton edge and the 180-degree backscatter peak, which the BecqMoni app incorrectly identifies as lutetium-176. Now let's take a look at the radium-226 spectrum. The energy measurement errors for the decay chain remain acceptable, being necessarily 0 for the lead-210 photopeak, since this peak was used as a calibration point. The errors also remain acceptable in this spectrum. And the same goes for this one. The values can be loaded into the device using the Save to Device CFG function. However, we will copy them manually. It is important that this coefficient is positive. Otherwise, it should be rejected and the calibration repeated using a different low-energy photopeak. And finally, the calibration is complete.